Hello and welcome. Today we are presenting an overview of the software Laoss for the simulation of opto-electro-thermal effects in large area devices. For example, AMOLED displays, lighting panels or PV modules. There are various fields of applications in which our software tool Laoss can be applied. In this video we'll be showing 4 main applications and the related simulation tasks in Laoss. The software allows you to understand effects that occur in displays such as pixel crosstalk and to optimize the device design in order to achieve the best efficiency, for example by modifying electrode layout parameters. Here we focus on the lighting and display applications of Laoss. OLED lighting panels should yield a homogeneous emission and keep the heat generation low in order to prevent degradation. Both can be achieved by optimizing the design, for example by suitable electrode materials or metal grid design. In displays, clearly defined colors with good angular stability are key. This is achieved by optimizing the pixel layout, their materials and the structure in between them. Laoss is a simulation software that can address all those challenges. Laoss consists of 3 different modules: electrical, thermal and optical. All of them have their specific fields of application. Let's start with the electrical and thermal module of Laoss. Before we show real applications, we will briefly explain the model and the necessary input provided by the user. The electrothermal part of Laoss is based on a finite element method. On the 2 electrodes we solve Ohm's law in 2 dimensions. They are coupled by a user-defined one-dimensional coupling law. Overall, this 2+1D approach mimics very well the 3-dimensional nature of real applications and is computationally much more efficient than a full 3D treatment. Laoss automatically runs a meshing and solves the partial differential equations for the system. As an output, the user directly obtains electrical potential distributions, IV curves of the device, and much more. As a user, you will first load the geometry, i.e. the top view of your devices. Laoss will run an automatic meshing, and then next the user defines the further inputs, such as the coupling law and the electrode conductivities. The simulation is ready to be run, and the user can explore the results within a few seconds. Optionally, one could now, for instance, modify the geometry and rerun the simulation cycle. As an alternative to the freeform definition of the geometry by a DXF file, Laoss offers a few predefined geometries that can be readily used. Current will generate heat. This phenomena is well known as joule heating. At places with higher current densities, one will measure higher temperatures. In order to simulate this effect, Laoss offers the thermal module, which has to be coupled with the electrical calculations. As a first and more simple option, there is only one way of coupling. Current will generate heat, which leads to increased temperature. However, the local temperature can also have a backward effect on the local current. This option is called full coupling and requires the user to set a temperature-dependent IV curve. When using the thermal module in Laoss, the user also has to set some more parameters which define the heat flow within an electrode or the transfer with the medium above and below the electrodes. These are typically well-known material parameters and can be looked up in literature. Let's now have a look at application examples that demonstrate the options of the electrothermal simulations in Laoss. The first example was inspired by an experimental work by a group at LG Display. When they switched on all the blue pixels in an AMOLED display, they observed that the red pixels were also lighting up, thus turning the display purple. This undesirable effect is well known as pixel crosstalk and occurs in displays which feature some common high conductive layers. Here, the whole transport layer is shown in yellow. Key parameters are the pixel density and layout, but also material parameters such as the electric doping densities. We have used Laoss in order to analyze and quantify this effect. In Laoss, we load the pixel structure as well as the individual IV curves of red, green and blue pixel. In order to mimic the experimental conditions, we also switch on all the blue pixels by applying the same voltage to all of them. Laoss directly calculates the potential distributions, here shown for 4 volt applied to blue pixel. Moreover, you can analyze the IV curves of the different pixels. There is also a non-negligible current in the red and green pixels. This is the crosstalk effect that we wanted to simulate. Using the current efficiency values, we can directly get the luminance values of the different pixels. Up to 40% unintended emission from the red pixel compared to the blue pixel is observed. Even if the effect decreases with higher voltages, this will clearly hamper the color gamut of the final display. In the next example, we look at an OLED lighting panel. When you take a closer look at the panel and remove the scattering foil on top, you can see a fine metal grid. This metal grid is necessary to achieve a uniform emission of the panel. One example of such a metal grid is a honeycomb-like structure, shown on the right-hand side. This grid is readily available in Laoss as a predefined geometry. We are going to use this in the following examples. Here on the left we show the simulated potential distribution without a metal grid. Clearly, the potential is non-uniform and drops to almost 5 volts in the center of the module. In order to increase the potential and consequently the luminance uniformity, a metal grid is used. Here on the right-hand side, the potential in the center is only about 0.2 volts lower than on the outer edge. Such a panel without a metal grid and the corresponding luminance distribution has also been characterized experimentally. The Laoss simulation agrees perfectly well with the measure profile. The parameters of the honeycomb metal grid can be varied and optimized automatically in Laoss. Here we show the potential distribution of a varied hexagon radius. With decreasing radius, we clearly see a more homogeneous potential, which would lead to an improved uniform emission. However, as the metal grid is non-transparent, it also has a shading effect. This effect is increasing with decreasing radius and could lead to a lower emission in total. The simulations in Laoss allow you to find the optimal configuration of your electrode. Another effect that has been observed experimentally is the non-homogeneous surface temperature of OLED lighting panels. Because of the feedback from temperature to current, this will also result in a non-uniform light emission, here shown on the right-hand side. We want to simulate this effect using the thermal coupling options in Laoss. For simplicity, we only simulate half of the OLED panel. You can clearly see that the temperatures are the highest in the corners and drop towards the center of the panel by about 40 degrees Celsius. One could now easily play around with some of the parameters in the simulation to check how this detrimental effect could be decreased. The third module of Laoss is the optical module. Again, we will start with the model, the input and the output quantities. Laoss Optics is a full 3D ray tracing algorithm, which is a Monte Carlo method. The idea is fairly simple. Some rays are launched from a specific area. Here the pixel is marked with a yellow rectangle. We then follow the path of these rays throughout the stack, which is defined by the specific layer and interface properties. Finally, we post-process information about these rays, for example at which XY position they exited the topmost interface. The stack in Laoss Optics is defined by a sequence of layers and interfaces. Layers and interfaces have specific properties which have to be defined by the user. The interfaces, for example, are defined by geometry or layout and topography. The geometry itself is further divided into subdomains, for example, the 4 pixels shown here. Each of these subdomains are characterized by reflectance, transmittance, and optionally emissive properties. There are several plots readily available in the results section of Laoss. The polar plot reflects the far-field intensity that could be seen by an observer looking at the device or a detector that is used for characterization. The XY shows all the rays that penetrate the last interface, independent of their angle of incidence. This view can be used to look at the microscopic scale. If a wavelength sweep is enabled, Laoss directly shows the apparent color and outputs the color coordinates. A special feature is the CIE color diagram, which shows the color point at the position of the cursor. The traces of selected rays are displayed in the sample rays plot, which helps the user better understand the observed effects. The user can also inspect the 3D structure with a movable detector. Upon clicking the refresh button, the intensity on the detector area is displayed. Now let's move on to the application examples generated with Laoss Optics. The first example focuses on optical pixel crosstalk. We implemented a similar structure as presented by Lee et al. In Laoss. In order to mimic the full display, we simulate the smallest repeating unit and use periodic boundary conditions. As an input, we have to provide the white OLED emission spectrum, as well as the optical properties of the different color filters. Our initial settings are used as a reference structure. In the simulation, we can now easily vary several parameters of the display or the materials used. For example, we can sweep the slope of the pixel definition layer. Here we see the XY plots of intensity and color as a function of the angle between the PDL and the OLED pixel. The crosstalk can be seen predominantly at the edges of the neighboring pixels. The intensity map is used to quantify the light leakage as the ratio between the intensity of the adjacent pixels divided by the intensity of the green pixel. Interestingly, the crosstalk is highest for a slope of 45 to 60 degrees. Laoss optics can also be used for inorganic lighting concepts. Here, a panel from Design LED is simulated in Laoss. The goal is to achieve a bright and homogeneous emission in a forward direction. In order to couple the light out of the top, a reflecting textured backplane is required. The structure of this backplane is now optimized using Laoss optics. The reference structure without any texture is only emitting into the right half of the upper hemisphere. The current solution used in the application distributes the light much better. By further optimizing the backplane texture in Laoss, an even more uniform light emission can be obtained. As the last example for Laoss optics, we show the simulations of a curved display. This display features inorganic LEDs sitting at one end that emit into the light guide. Also here, a homogeneous light emission in a forward direction should be achieved by a specific texturing of the two curved interfaces. Different scattering structures have been tested in Laoss, which lead to pronounced differences in emission. Again, an optimized structure can be obtained from optical simulations without the need for time-consuming fabrication. So today we've shown you the potential of Laoss simulations for lighting and display applications. The three modules and various examples have been presented to demonstrate the advantage of using Laoss simulations. Further information about Laoss can be found on our website, fluxim.com. There you'll also find a link to apply for a free evaluation license. You can contact us by phone or by email, and please remember to follow us on LinkedIn and Twitter. Thanks for watching.